In class today, you did a lab called Mass versus Velocity of Molecules. And you used this lab sheet right here to collect your data and to tell you exactly how to do everything. When we go on, what your job is tonight is on the back of your paper, you're going to be showing the relative rates that are calculated using Graham's law. So in question 7, you're using the actual counts for the relative rate. In question 8, would you all look at your lab sheets? In question 8, you're calculating the relative rates based on the molar masses of the molecules. So there's two sides of that Graham's law. Let's go back and look at those guys again. Here, whoops, not there. Come on, where are you? Yeah, where did I put them? There it is. Okay, so here's the Graham's law of effusion. Elements are inverse. Okay, in this case, we're using elements and sometimes molecules, or you would call it compounds, and that is with your methane, the CH4. But your first thing that you're calculating is the chlorine to hydrogen ratio, and that is their rate ratio. And that could be calculated by using their molar masses, or you can use our little computer simulation, and you can compare the rate of count from the chlorine and the hydrogen and be able to get those numbers. So tonight, when you finish things off, you want to know that this thing over here called rates is the observed, or what you actually did on the computer by counting how many times the molecule hit the side of the container. And over here, you have enough data right now because you've already calculated these molar masses. I don't want you going to a computer before you have, because you need to know these guys just a little bit in terms of what their relative masses are. Okay? And I think that's all I had on the screen. Yes. So as we go on, the next screen is going to tell you, come on, there we go, how you're going to get the rate of hydrogen to chlorine numbers. Okay, when you do your counts on the computer, or when you did your counts, if you've already done this, your rate is going to be in terms of how many times that molecule hit the side of the container. We call that the counts. And then the rate of hydrogen is the same thing, it's just a different molecule. You're going to take those two guys and divide them out, and you'll get, in this case, a decimal number. Now, on your computer, these numbers could be very different. Okay, this one might be a little higher, this one might be a little lower, whatever, but it'll probably be somewhere in that range. This number is more likely than not going to be different than the number you get when you take the molar mass of each of these and divide them and take the square root. See, this is the right side of Graham's law. And let's get these guys side by side here so we can see this and make sense of it. Let's get one more screen over. There we go. Oh, yeah. Here. That's fine. So here's the Graham's law formula, and here is what we're doing in the lab. You can see all I did was take out the equal sign that's between these two guys and break these things up, because I want to see, or I want you to see, how calculating the rate of effusion using the molar masses is going to give you a number that may or may not be different than this one. So that's what we're doing in your calculations when you're done. Then you're going to do the same thing with this guy. Okay, and this guy, and this is all, by the way, on the back of the top half of your page. Okay, so this should take up the whole top half. And those of you in the class right now, you want to take a picture of this screen here so that you have it, so when you're doing your calculations at home, you can actually look at it. So this left side over here is getting the relative rates based solely on the counts that we get when we do the lab. This guy over here is based completely on the periodic table and the numbers that we get there. And so what we're going to do is we're going to compare those as we go to the next part. So the back side of the sheet, the bottom, you're going to do a percent error calculation, and those of you in class right now could take your picture of this screen. Okay, what I'm exposing right now is the bottom half of the last screen you were looking at, and this is your theoretical, which is calculated from molar masses. This is your actual that you get from your counts. There, that you get from your counts, and then you've got theoretical again down here. And these again, these theoreticals are what you're getting from, let's split the screens again. Theoretical is what you're getting from this side of the screen. Okay? So when you're calculating the theoretical and everything being used over here, you're getting a percentage of error. And the theo is this right side of this screen, and the actual comes from the left side of this screen. And the left side would be question 7 being answered, and this side would be question 8 being answered. So because you're doing two different ratios, there's a ratio here of chlorine to hydrogen, and there's a ratio here of methane to nitrogen. And so each of those will have a percent of error, because we're going to have rates for methane, nitrogen, and we're going to have molar masses being the basis of calculation for the relative rate on the right side of Graham-Cracker's law, right? So we do that one with the methane, nitrogen, then we're going to do it with chlorine and hydrogen. So we're going to have two different percentage of errors. And I hope that's clear. I'm going to open for questions, and if anyone in the class wants to ask a question now, this is the time. My 6th period has just certified to you that you have learned everything you need to learn to be able to do your lab write-up. So that's the end. Thank you for watching. Hope this helped. Okay, so the student has finished the lab. He brings his paper up to me, and he's got the Graham-Cracker formula here. I mean the Graham's formula. And and then he says, is this right? Well, there is no right. There's only what you do. Okay, the only thing that I might have a little bit of concern with is that we only have 2 sig figs here and 2 sig figs here. It would be better if we wound up with a total of 3 sig figs. So your counts are actually infinitely accurate. Okay, so this could be 50.00 because you're counting in even singles. Okay, this could only be 3 sig figs. Okay, so we could give this guy another 0, and we could certainly give this guy more sig figs, because we had a 1, 2, 3, 4, 5, 6 sig fig number here, along with a 3. So when we did the division, we should come out with 3 sig figs, right? Okay, so that's the only way in which I would say that this could be improved. So assuming that the molar masses were done correctly and that the square root was done correctly, this is reasonably accurate. Okay, so now when we run our other stuff back here in the real world, let's get back to just a second. So now we have to look at our percent error. When we look at the percent error, the theoretical is what we get from the right side of this screen. The actual is what we get from the left side of this screen. So we're going to plug the theo, this number, subtract the actual, which is this number, and then we would have, when we multiply by 100 and take it as absolute value, which is what these verticals are for, then we would know that we have our percent error. Over here, we've got to do that same thing a second time. So the student's paper that I just showed you had half of the write-up. Okay, so we're trying now to get the write-up for the other half. Notice that the counts for both chlorine and hydrogen, as well as methane and nitrogen, that's question number 7 on my live sheet. Question number 8 is derived from getting the number that we get from the right side using the molar masses of this guy. You see, this is the right side, left side. In this screen, I've separated them. This is the left side, right side. Okay? But they're the same thing. They just don't have an equal sign because we don't have to find the missing number. This time we're just comparing the rates that we get from counts to what we get by calculating the relative rate using the molar masses, which is the right side of Graham's law. Okay, I hope this helps. See you all tomorrow in class. Okay, we're not quite done. I got another question from someone afterwards, after I stopped the video, and so I restarted the video, and this 2 times. What does that mean? We're doing it once for the chlorine hydrogen, which is this set of data, the top set. And then we're doing it a second time for the methane versus nitrogen, which is the bottom set of numbers. Okay, so everything that you need to do the relative accuracy of what we're doing here is going to be told to you by using this number or this formula and plugging in the numbers first from the top row and then from the second row. And that's why I say 2 times. Now I think we're done. Bye-bye.